Hi everyone, let's continue with our paths. And today we're going to talk about circuits, two special types of circuits, Euler and Hamilton circuits. Now, a little caveat, this is not my specialty. I'm an algebraist and a logician, but graph theory is a bit not used to that, and so sometimes I get confused and call one the other, and I think in another video in passing it was not relevant, but I might have said Euler where I should have said Hamilton. So figure it out yourself at some point that I have used it incorrectly, but here I will use it correctly. And what are we dealing with here? It's the problem that, okay, let me just start from a very simple example. Suppose we have a graph, say, with, I'm just going to draw a random graph here, a little bit randomly a graph. So let's say that's my graph here. And let's connect this guy too. And so there are two things we can, a circuit, we know what the circuit is, right? And there are always circuits. That's, well, I shouldn't say there are always circuits, but for instance, here a circuit would be you go from here to there, to there, to there, and you come back. And that is a circuit of length 4. Okay, so, and we have, we know actually there is a way of calculating it using the adjacency matrix and then the powers of the adjacency matrix. Unfortunately, it doesn't tell us the simple circuit. So when I use Euler and Hamilton circuits, here I always will mean simple circuits. Whereas the number that you calculate by using the powers of the adjacent matrix are any kind of circuits. So you have to, that's a little annoying. So the calculation of the number of circuits of a particular length can be a little bit tedious, but it can be done. But what we're now interested is, well, you could say perhaps the longest circuit. Is that interesting? Yeah, sure, it is. But we're going to focus on two conditions, two different conditions, and obvious conditions. The first condition is, well, I want a circuit that visits every vertex, or I want a circuit that uses every edge. Now, remember, the circuits are simple, right? So when I say use every edge, it can only be used every edge exactly once. And now is the question, do they exist, and if they exist, how do we find them? And so Euler, what is this? And what is a bit strange is, if you had to, if I ask you, okay, now you pick one of the two conditions, which one would you prefer to deal with? Visiting all the nodes or of using all the edges? What do you think is going to be the easiest? And I think I at least would have said, oh, the vertex problem. And actually it isn't. It's the edge problem is easier to deal with. And so we're going to do with that first, and that is exactly Euler. So Euler is about visiting or using all edges. So I'll put it here, using all edges. And Hamilton circuits is visiting all nodes, all vertices. So if you think Euler is edge concentrates on edges, Hamilton circuits concentrate on vertices. And I sometimes have to remind myself which is what, so perhaps we could say Euler edges, but Hamilton vertices doesn't work, so okay. But there's another way that I kind of remember it, because there's a reason why they're called Euler and Hamilton, by the way, are two people that were interested in graph theory, and in fact Euler is probably the father of graph theory, because Euler was looking at the problem, the following problem. So let me, I gave you a quick introduction of what everything is, but I will give everything more in detail when we get to the actual juice of the meat of the problems. So Euler lived in a place called Königsberg, which is I think in Russia nowadays. It's Kaliningrad, Königsberg, but at that time it belonged to the Prussian Empire. Prussian, Polish, German Empire. König, by the way, is just the German word for king. And Berg, I'm not sure, Berg might refer here to a fortress or might refer here to a mountain. I'm not exactly sure what it refers to. But anyways, it's the name of a place, Königsberg. Kaliningrad is it called nowadays. and which is actually the literal translation of Königsberg. So okay, yes, right. That tells me that Grad means Berg here means stronghold. So the king's stronghold. Okay, and so it has two rivers that flow through it. So I'm gonna draw my rivers here in blue, I guess, right? Blue water. So one river runs this, and it comes from there. It's basically no, it's one river, but it bifurcates like this. I guess the better way to say it, it's two tributaries that come together. They kind of connect here, but then they also finally become one single stream going out of the city. Okay, so that's how the stream looks like. Now, of course, this is a city built on top of these rivers, so there are going to be bridges over these rivers, right? So let's let me first call the bridges here. So there's a bridge here. So this is bridge 1. But there's actually two bridges here, one bridge here. There are also two bridges here, one bridge here and one bridge here. And then there's a bridge that connects these two areas. And then finally there are two bridges here and here. So there are 7 bridges, the 7 bridges of Königsberg. That is Euler living there. And the people in Königsberg, like I guess everybody likes to take strolls in a nice summer evening or autumn evening. The weather is getting worse nowadays, but at the time, and when there was no social distancing and all that, so they would like strolling, and they like their city, and they want to visit. It was a rather small area, so they could walk, and they like the bridges. Of course, I mean, people always like bridges, right? The water flowing, the ducks going underneath it, and you see little fishes swimming, and perhaps a beaver and some stuff like that. So they like to walk over the bridges. And so the question always was, is there a way to walk through the city and go over every bridge exactly once? Okay? So in other words, okay, you would say, I don't know where you start. That's the problem even was said, okay, if you lived here, that might be a different question than you lived here, or you lived here, or you lived here. So you can start in one of these regions. I'll later will give names and something to it, but so for instance, you could say, okay, I'm going to go this way, and then that way, this way, that way, this way, and then this way, and then that way, and this way. But you saw, I didn't made it a bit quick, but I hope you saw that some bridges I crossed twice. So I can cross every bridge only once. And so, in other words, it's not obvious. There's no obvious solution. Okay, there are sometimes, if there would be much less bridges, there would be an obvious solution, but there is none. So people were asking this, and Euler, people were frustrated because they couldn't do it. So Euler wanted to show rigorously that it couldn't be done, and he came up with the idea to use graphs. So what are we? And the clever thing about graphs, some application of graph theories, is to decide what are your edges and what are your nodes. Okay, so here we have the bridges. You could say, okay, I make a bridge into my vertices, the nodes. But then, what are the edges? Or what else can I do? And that's what we're gonna do. There are actually the river cuts the city in 4 quarters, right? So you have the central quarter A, and then we have the north here. We have the east quarter. Let's call this C, and we have a quarter D here. Okay. So I mean to say B is all this, D is all this is A, and all this is C. Okay, that are the 4 regions cut out by these 2 rivers. And these will be my vertices. And there will be an edge between this vertex and this vertex if there's a bridge connecting them. Let's try to implement this. So we have A, B, C, and D. So A, yeah, I like to call everything with small letters. Let me use lowercase here. I'm copied the use of the book, but I like to stick my own. So let's call this A, B, C, and D. So this is A, B, C, and D. Again, does it matter how I put these vertices? No, it doesn't, because that's the beauty of graphs. The edges, that's what matters. So let's see. We have an edge from A to B because there's a bridge. Actually, there are 2 bridges. What should I do here? Is that important? Yes, because I want to walk over one bridge and over the other bridge exactly once. So what you see, what we're going to get is a multigraph. We haven't used that much multigraphs, but they are useful, and in this case, we need to consider that. So we have two edges from A to B. And notice they are not directed edges. This is not a directed graph because I don't have stipulated that you have to walk with the bridge this way. You can walk with this bridge that way, but you can only do it once. Okay, so we have from A to B, there are two. What else do we have? From A, we can go to D, which might be gotten a little bit sickish. So from A to D, with two different bridges. So again, two different bridges. That's that. And what from A, I can also go to C. There's only one bridge there. Okay. What else? From B, I can go to C. There is only one bridge connecting the two. That we're talking about this bridge here, right? It might B is this whole area. Don't forget. So there's also a bridge there. So from B to C. That's it. From C, there are the bridge to B. I have that already. A bridge to D, that I don't have that. And a bridge to A, which I have already. And then finally, from D, I can go two bridges to A and one bridge to C, but I think I have everything. I should have, there are 7 bridges, so how many edges should I have? 7, right? 1, 2, 3, 4, 5, 6, 7. Okay, I got there. So, and now let's remember what I said was an Euler circuit is. It's a circuit that visits every edge. So what does it mean to visit every edge in this situation? If I go from A to B using this edge, that will be the same as going from region A to region B, going over the bridge that corresponds to the edge. I could have named these bridges and I could have named the edges, but it's not important here. So I'll defer from using names here. Okay, so yes, so a crossing of a bridge corresponds exactly to an edge. That's what it is. And so what is an Euler circuit would be a path, a circuit, not only a path, but a circuit that grows sorry, that goes from one of the vertices and starts using all the edges and then returns. Right? Something like this. So, but you see, I'm kind of cheating because I went back and forth on things that I'm not supposed to do. But that would be a circuit that would correspond to a walk through the park, so to speak. Well, yeah. See, you can see that it's almost doesn't work well, right? Okay. So, and so if you use it with graphs, you can. So the question becomes: can the citizens of Königsberg do their ideal walk? Corresponds to is this graph, this multigraph has an Euler circuit? Okay, and the answer is no. And so I want to give you exactly the solution already, because the solution is also the part where it's more than just telling you yes or no. It's also going to give us, if it exists, how to do it. And so here's the criterion. So G has an Euler oops, that's not how you write Euler. An Euler path, even only if, so this is a sufficient and necessary condition. If you still remember what this is from discrete man, that one, it means if you have an Euler path, then what I'm saying is has to hold, and vice versa. Even only if it's easier to state it the other way. If there are no odd degree edges. No odd degree, vertices. So it is strange, right? It is about edges, yet the criterion is on the edges. So no odd degree vertices. We had seen something about odd degree vertices, right? What do we know about odd degree vertices? Their number is always an even number. But now we don't want it to be even, we want it to be 0. And then we have an Euler path. And only then. That's what it says. If you have an Euler path, then this must be true. Oh, sorry. If you have an Euler path, then this must be true. And if this is true, then you have an Euler path. So let's see in our case of Königsberg, the Königsberg graph, what we have. I'm going to list the degrees. 1, 2, 3, 4, 5. Okay, here it's already, forget it. Degree 5. This has degree 3, this has degree 3, and this has degree 3. It's absolutely not, if instead of having no odd degree vertices, they're all odd degree. So it doesn't exist at all, and unless you swim or jump or whatever, you're not going to be able to do this. Okay, or by building perhaps an extra bridge, you might try to solve some of the problem. But you see, you have one bridge. What will that do? Well, it will change the degrees of at most 2, right? A bridge is an edge, so at most 2 will change the degrees. That will still be left with 2 odd degree vertices. So okay, so I'm going to build this bridge, and I say, okay guys, I see this is a problem. The mayor says, I'm going to build you guys the following bridge. Let's say I'm going to build a bridge from a super bridge. Oh no, I'm going to build here. Here is my new bridge. So this is now in a different color. So this would be here, and this becomes now 4, and this now becomes 4, right? There's now one more edge, and more the degrees have increased. So still the same problem. But oh, sorry. Oh, whoa! I forgot. I said Euler paths, and this is exactly what I shouldn't have written here. But we're talking about circuits, right? I'm sorry. I always these two words I somehow keep. Oh no, I want it to be in black. So Euler circuit, and I repeat, it's a simple circuit because every edge can be only seen, visited once. So the new graph with the mayor with this one bridge, not gonna work. But there is a second thing, and this is exactly where I was so upset with myself that I wrote what I wrote. G has an Euler path, and I have to say what it is. I'll say in a moment what an Euler path is, even only if, but I should add, but no circuit. So I'm weakening the condition of circuit to that of path, even only if there are 2 odd degree vertices. So what is an Euler path? So remember, Euler circuit means a circuit that uses all the edges. Well, an Euler path is exactly the same. It's a path that uses all the edges. What's the difference between a circuit and a path? A circuit has to start and end at the same place. A path doesn't. So that is why this is a weaker condition. It means like, okay, you start in A, and perhaps by walking you end up in D, but you have visited every edge, every bridge. You walked over every bridge exactly once, and so you have accomplished at least the visit, the condition along the bridges. Unfortunately, you have to stay over at your cousin's place because you live in place A. So that's the problem, the difference. An Euler circuit means you come back to where you started. An Euler path means you start from one place and you go to the other place. And when there are exactly 2 odd degree vertices, and in fact these 2 will be the start and ending point of your walk. So in this case you can start, and it doesn't matter which way, because we've seen paths are undirected, so you can any path or any circuit you can walk in one direction, and then you can basically trace back your steps and walk it in the other direction, right? So you can go and so you can start at C. So what this theorem says, the second part says, if you have this additional bridge, which we didn't have an original problem, but with the additional bridge, the mayor has at least made the opportunity for his citizens to go from C to A, or from A to C, visiting every bridge or passing every bridge exactly once. You say, okay, if that's the case, how? Now, I'm not going to solve this yet. So I'm leaving it here. I'm going to start with this guy here and solve problems on this one. Okay, I'm going to, first of all, let's give an example of something that has actually this property, right? I mean, you might say, and although I am applying this on this multigraph, I'm going to work mostly with simple graphs. But this criterion works as well for simple graphs as for multigraphs. I should have added they have to be connected. Okay, this is for connected graphs. Okay, but let's not dwell on that. that makes sense, right? If a graph is not connected, so what does that mean? Remember, this means you would have something like this, right? You have, like, say, oh, sorry, we have this, and perhaps this, and then we have this and this. This is a graph, but it's not connected. So it's impossible to walk, to have a path that will cover every edge, because if you're in this part of the graph, you're never going to go to that part, so you'll never be able to walk on any of these edges. So for a disconnected graph, the answer is trivial no. So that's why I'm not insisting that I have to say this actually is only true for connected, but I hope that is not a problem here. Okay, so but going back to our some examples. So here's some examples. Here is an example. So let's do. I think it's this kind of butterfly thingy. Yeah, this is an example. And so let's calculate the degrees. 2, 2, 4, 2, 2. So we know by the theorem there has to be an Euler circuit. And let's think about now. A circuit is something that starts and ends at the same point. So you still have this option, where should I start? Even if there's an Euler circuit, does it matter where I start? Think about this for a sec. The answer is no, because you're going through every edge, right? So you're gonna also therefore visit every vertex. Therefore, it doesn't matter where you start. If you start at one, you will pass to the other, and instead of starting at the one that you started, you can now start at the other vertex, and you will still have the same path. It's just the starting point is just different, but it's all one long circuit that connects several vertices. So, so the starting point doesn't matter. So we know that there is going to be one, and so let me give names here. So I just have to write down one. And again, this doesn't say that there is a unique circuit. There might be several circuits, but there is one here, and here is it's so small that we can see it. I think 1, 2, 3, 4. Oh, this does this all the time. It thinks that I'm doing something. 2, 3, 4, 5, 6. You see, I did exactly what I promised. But if you can also go, there are different things that you can do. So let's write down what the path is. A, B, C. I forgot now how I went to D, right? I could have gone to E there. You see there are some options there, from D to E, from E to C, and from C to A. Notice that I visited C twice. Okay, yeah, of course, you shouldn't say I visited A twice, because this is this end and this is the start. I actually only visited once, if you want. But the C has been crossed twice. That's not surprising, because it actually is the one with the highest degree. Okay. By the way, if you have something of degree 2, how many times are you going to cross through it? Well, only twice, right? Or only once, because you have 2 edges. One edge will bring you inside, and the other edge will bring you outside. We don't know which one is what, but that's the thing. Okay. And in fact, from this you can actually see how many times will you cross C. Well, you have one time. One of the 4 edges will bring you in. One of the 4 edges will take you out. That's 2 of the 4 are gone. And you can now, with the 2 remaining edges, you can argue the same. So in other words, the number of times that your cross to a particular vertex will be the half of the degree. Okay, that's an extra information that you have, and that might be useful to find the graphs. Okay, so this is one example. Here is an example where it doesn't work. Let's see. I will do this one here. This one has also 5. Okay. So here we have this. There's 2 triangles inside here. Okay. So let's call it A, B, C, D, and E. let's calculate the degrees. Degrees are 3, 3, 2, 1, 2, 3, 4, 2. So now we are in somehow trouble because we have 2 odd degrees, but that is exactly the situation that is described here. Right? So whereas this means there is no circuit, there will be a path. And we have said this, we will have to start and end in those 2 vertices with odd degrees. So the Euler path will start in A and end in B, or if you walk it the other way, it's the other way around. So that tells me already I shouldn't start from here and try to find the path. Okay? So this might be a little bit trickier. I hope I'll do it from the first try. So I have to start from A, that's what I said. So from A to D. So now I'll go back to A, I go to B, this, and I end at B. I should have in the meantime listed everything, but I didn't. So let's see, what did I do? From A to E to D, then I returned to A, then I went to B, from B I went to D, from D I went to C, and from C I went to B. Notice that I started A and end in B. Okay. Coming back to, we visit this once how many times? Well, D has degree 4, that's why it's there 2. Now, but notice B is also visited twice, and so is A. And I will explain later why that is. Because the solution to, if one of these conditions is satisfied, we will give an algorithm to find actually the circuit or the path. And that will be related to what I'm going to say soon. Okay, so I want to now give an example. I'm not doing the part on directed graphs. I'll leave that for the readings for you. So I want to do a little bit of let's see, where is my graph that I had here? No, this is not the graph. Sorry, I have to look for a graph that I had. Okay, I'll make up a graph. It might be easier first for me to do here. So I'm gonna do this. Oops. 1, 2, 3, 4. Okay, so let me do this. No, 4, and then I will do 1, 2, 1, 2. Okay. Then I will have the square here, a triangle here, and a triangle here. Okay, that's what I will look at. So let's first calculate the degrees, see whether it actually makes sense what I said. So this was 2, 1, 2, 3, 4, 2, 2, 2, 4, 2, 2. Okay, good. So it satisfies the circuit, Euler circuit criterion, that no odd degree vertex. That's splendid. So we know there's a circuit, and we also know that it doesn't matter where we start, because we're going to go through all the vertices. In fact, we know how many times this vertex will be visited once, this will be visited twice, once, twice, once. Half the degrees. And this is exactly what we keep in mind. We come in and we go out. That means 2 of the edges will no longer be used. And that's exactly what I'm going to do. So I'm going to pick randomly one of my vertices, and let's pick this guy here. Let's give them names: A, B, C, D, E, F, G, H. Okay, I'm going to start from A, and what I'm going to do, so procedure. It is a procedure. I'm not even going the algorithm. Let me write it algorithm. That's perhaps better. The algorithm, but I'm not going to present it in pseudocode. The book has it in pseudocode, but I find it a bit hard to read the pseudocode, so I'm just going to explain it. So step 1 is pick a vertex. It doesn't matter which one, pick one. I pick one, I pick A. Okay. So step 2, pick a circuit starting vertex, let's call this V. Pick a circuit starting at V. So with the pick that I use, I pick something and then I pick a circuit starting at V. Now, you might ask, is it possible that there is a circuit at V? For instance, let's look at a graph like this here. Suppose this was V and I go, this is my graph. Is there a circuit that starts from V? No, because what's the problem with V? V, if I go out, there's no way to come in because I cannot use this edge anymore, right? What we're gonna do is in our algorithm, each time we use an edge, we're gonna kind of delete it or scrap it out. I'm a bit worried about my delete. I was a bit careless. I'll try to do the delete part, but so that tells me it's not guaranteed that you can always return. And so the condition that allows you to return is exactly the even part. Because, see, each time you go to a vertex and then leave the vertex, you will have exactly used two edges. So if you now remove those two edges, so let's do this, right? I'm going to start from A. So I'll work out the algorithm as I'm explaining it. So this is I'll write the algorithm here, and here I do it on my V that I pick is A. So I pick A. And then I'm saying, okay, I'm going from A to D. So A, D, that means this is now gone. And then I can go, whatever I do, I just go to E. I just pick something. I go to E. That means I can no longer use this vertex. Oh, see, that's what should have happened. Okay, I have to be a little bit more quick. So this one is still there, right? This one is still there. I hope I didn't erase anything else. Okay, yep. So I'm in E. In E, look, E is a vertex of degree 2. You come in and there is that one you cannot use anymore. There's only one door out, if you want. There are two doors. Think of this as this way. Edges are the doors that you come in, but every door, they're all on ajar. But once you go through a door, the door clicks and is locked. So if I walked into E, if I walk into E, I have used this door and it's now close to me, so it's gone. And the only door I have left to leave E is this one. So, okay, so I go to B. That means now this edge is gone. And again, I still have choices here at B. I can return to A, or I can go to C. Let's say I return to A. I kind of want to make a circuit. I was a bit worried. I'm worried that if I don't return, then I might not have a circuit. Remember, I have to end back in A. And I see A and I think, okay, I'm there. I don't want to risk it. But actually you can. But I don't want to risk it, so okay, I'm going back to A. Okay, so you go back to A, that means you have got this one. Okay. We have a circuit, but it's not the circuit that we want yet because there are still edges that we have not traveled to. Okay, so what's the next step? And this is an important step to understand. Some of the vertices that are remain belong to the path, the circuit that I already have. Some don't, right? So let me remind you which of the vertices. So these are. Let me also mark the vertices that I have visited already. You see, these are the vertices that this path. These are these vertices, right? Notice that the two blue vertices that are still have edges coming out. So pick one of those. So pick a vertex from the old path, from the old circuit, from the circuit that you just made, or made before, because we're going to do this several times. So pick a vertex from an old circuit. Okay? In this case, it means pick one of the blue, but of course, only those that have still edges. Pick a vertex from old circuit that is not isolated. Let me not say that. Okay, it's stupid to take that, right? I'm not going to take A anymore because I'm done with A. So perhaps let me even emphasize this by saying, okay, I cannot go to A anymore, I cannot go to E anymore. So pick a vertex of the two remaining one. Let me pick B. So I'm picking B here. So I'm picking B. Notice that what I'm going to do now is the same thing and go back to this. So this is the new V. So pick a vertex V. That will become the new V. Right? Each time I use a new V. This in this case is B, and I go back to step 2 and do the same thing. Why can I do this? Well, let's see what happens to the degrees. Perhaps that would have been better if I would have done it this way. The degrees have changed, right? Because this has now degree 0, this has degree 2. I came in and I went out. So 2 doors were closed. Only 2 doors are closed. Here, 2 of the 4 doors are closed. Notice that because of what I just did, is always subtracting 2 from the number of degrees. The remaining graph still has the same property that every vertex has an even degree. The only thing it's not connected anymore, but that is something that I ignore for the moment. Okay, you'll see why. So I do the previous thing. I started B. So here are 2 choices basically. Let me go this way, or let me do this in black. So I go. Let's go across and then down and then up again. So, so this means I have visited now these 2 also. I visited these 2, and the edges that have been used are this edge, and this edge. Therefore, the new degrees are 0, 0, and 0. Okay. And look, I'm step 3 now. Pick a vertex V from an old circuit that still has a positive degree. That's kind of obvious, so I'm not going to state that. What can I pick? There's only one choice now, right? So I remember, where am I? I picked a vertex, that was A, and then found a circuit containing A, that was this circuit. And then I was in step 3, pick a vertex V from an old circuit, that is B. And then I went back to step 2, where I picked a circuit starting at V, that's what I did here, that's this circuit. Okay, and I'm back in this position, right? In step 3, it's like it's a loop here. This is a loop part, right? We loop from 2 to 3 and keep going until there's nothing. Until here we cannot do anything anymore. But we can pick a vertex V if it exists. Or should I add that here from an old circuit? So I can the blue ones, but the only blue one that is left is D. So I cannot put G and H. I have to choose D. In this particular case, it doesn't really matter. But here I have to choose D. And then, once I make this choice, I go back to step 2, where it says just pick at random, start walking. It basically says start walking until you see yourself again, until you're back. This is just walk randomly until you're back. And you're guaranteed to be able to do that. But of course, each time when you enter a door, you close the door behind you and you cannot use that door anymore. But the even degrees make you able to return back. So here it would be from, let's say, again, let's go down first and then across and then up. So that would be this path. And so also this is gone. Now you say, you have 3 circuits, Professor. That doesn't work. Right. And so what I'm going to do is I'm going to say, remember, the one that I picked here, the B that I picked, is already from my previous path. So I can insert it here. So I'm replacing this single B by this whole path. So instead of, so what this path says, okay, when you're in B, you go to A. You come from E, and then when you're in B, you go to A. Now I'm saying, okay, when you're in B, wait a sec. Don't do yet what the path says. Do first the other path. Go around, because it's okay because you come back to B, right? That's what you're going to do. And then you do the same thing with the next one. Since by choice, this is a vertex that was already used before, it could have been in a part of this vertex. Okay, it is not in this particular case. We'll see other examples where it might be. So now we say, okay, this vertex, that is this guy. So I do the same thing. I replace this D by this little. When I'm entering D through one of the door from the door that comes from A, instead of going to E, I'm saying, okay, I changed my mind. I'm going to go first around and then I go to E. So what is it? So let's write down the whole path. A, D. Now remember, in D I decided to make a little detour, the GHD detour. Okay, now I'm back in D, and now I can continue E, B, and say, oh, B is the one that I also want to do detour. So C, F, B, and then now back in B, I continue A. And so here is the Euler circuit that connects them all. So this would be, I know the edges are gone, but I hope you A, D, from D I go to G, from G I go to H, to D, then I take E, then I do the B, C, here it goes again, B, C, F, B, A. I visit every edge exactly once and return to my starting point. Very nice, no? Okay. So, and this algorithm works always. So I'm going to leave that to you. I'll do another example. But I want to now say, how can I use this algorithm to get an Euler path? And specifically here in the walking problem where the new city of the new Königsberg, the new mayor want to make a fame for himself and build one extra bridge. And now we are in a situation at the 2 odd degrees. We know that we have to start at one and end at the other. And then we will be able to walk all 3 bridges. But it will only go from this part of the city to that part of the city. That's the only one way we can do it. It's strange, right? This actually, if this bridge was made between the 2 other ones, but somehow it's these 2 now. That's exactly what happens. They are the only odd ones again. How do we solve this? It is a very clever trick. And it's basically the same trick that the mayor did. Let's invoke a super mayor. And the super mayor is a virtual mayor. Let's make a virtual mayor. And the virtual mayor says, okay, I'm going to build one more bridge. A bridge between the 2 odd degree guys. So I'm building this bridge. I'm doing it in dotted lines because it's not an actual bridge. It's a virtual bridge. So that would be from C to A. So this means that bridge has to run somewhere here. Okay. But I'm planning the bridge, but I'm not going to put it there. But what has happened if the bridge would have been there, then this would have degree 6 and this would have degree 4. So everything now has even degree. Okay, so let's build a Euler circuit because we know it can be done. But this time in my first step, I'm going to be more careful. The first step, pick any vertex. Now I'm going to pick one of the 2 that are odd. Let's say C, or let's say A. And what I do then is exact same procedure, but there's one other proviso. The green is a virtual bridge. I'm never going to take it until the very last step. Let's think what that means. If suppose I can do that, what I'm just said, I'm going to keep my green bridge for the last. So I have this circuit. I'm going round. I end in C, and there's only the green bridge left that will me bring back to A. So what is my Euler path now? Well, the same walk, except for the last virtual walk that was not possible anyway. Now, which therefore has me stranded in C. So this return bridge doesn't exist. I'm stranded in C. But I went from A to C, visiting all the bridges, except for the virtual bridge, which doesn't exist anyway. So, okay, so let's solve it actually for this thing. I'll erase my thing here. I'm a bit worried that if I do this, I'll see whether. So I'm going to draw it on my. So I start at pick. We have to pick, and I said one of the 2 we have to pick. One of the odd degrees. I'm gonna. What do you guys say? Anybody suggestion? Of course, you might shout and holler as much as you want. I'm not going to hear you, so I'm picking A. So pick A. That's my first start. And now I'm going to start randomly walk, but except I cannot take the green bridge because it's not really a bridge. Okay. So here I'm going. And I'll do it here first on, I'll do it in a different color. Let's make it orange. No, orange is already one of the bridges here. So let's make it purple. So I'm in A and I said I'm going to go this way. Remember, I have to come back. Okay, this is me coming back. So what I do, let's erase. So perhaps I should draw, okay, sorry. because no, it doesn't matter. No, it doesn't matter. Okay, so let's see what I've done. I went from A to B, so one of these edges is now no longer available. Then I went from B to D. Well, there was only one bridge. That was the new bridge the mayor built, so that one is no longer there. And then I go from D to A, so that is one of these two bridges that I used. Okay, let's adjust the new degrees. This now has degree 3. Well, it has degree 4, right? Because of the virtual thing. This has degree 2. This is now degree 2, and this has degree. Oh, I changed that, so there's still degree 4 here. So perhaps I should do this in green, because this is now the green. Let's put here the green degrees, right? So okay, I'm gonna put them in green. So this is now degree 4, degree 2, degree 2, and degree 4. Yes. Okay. And what was the other condition? I have to use one of the guys that belong to the previous path. That was A, B, or D. Okay, so let's perhaps again also put already the ones that I visited, so that I don't get confused. I went to A, I went to B, and sorry, only one, and to D. Okay, so one of these I have to now start. I could start from A again, but I'm going to be like, I don't want to do that. I want to start from D. Okay, you do that. So before I do that, let me write up my path, because before I forget it, I went from A to B to D to A, right? That's the path I got. Now I'm pick. So this is step 1. Step 2 is picking this thing. Now step 3 was picking. Remember, what was this? Picking one of the vertices that belong to the previous circuit, or the previous circuits that you had. Well, all 3 actually. So I kind of can pick whatever I want. I'm picking D. So pick D. But I could pick the other ones. I'm not saying that that's a wrong choice. Okay, I pick D, and now I have to go back. So step 2 again. Step 2 twice. The second time I do step 2 is I walk around. So where am I? I'm in D. Yeah, you say, Professor, yeah, but are you not trying to make a complete walk? Yes, but not yet. At the moment, I'm not writing down the purple these are my little walks that I'm all going to put together in one big walk. So, okay, here's my purple walk. Again, the second, let's make this a different color then. So this was this walk. Let's make the other walk in pink or whatever this is. So pick D. Where is D? I'm in D, and I cannot use that bridge anymore. I'm going to go this bridge. So I'm going to D, and then I'm going to C, and B, and A, and D. I like this walk. Look at that. That's a nice circle walk. So what is this? Well, I started in D, then I went to C, then I went to B, then I visited A, and I returned to D. So now I have the edges. Which edges are these that I used? I do it in different patterns so that you can see everything. I want to keep all the information as much as possible. So from D I went to C, so this one is gone. Then from C I went to B. I cannot do this anymore. From B I went to A, use this. And from A I went to D. Here we are. Okay, so we have visited. Let's walk out everything that we have visited. The green is... we also now, in addition, we also visited... See, actually, we have visited everything now. What are the new degrees? Let's also adjust those. This has now degree 2, right? Everything that I visit has degree 2 less. This will now have degree 0 and degree 0, because I came and I went. Okay? So, this has degree 2. You say it has degree 1, Professor? Yes. In the original graph, it has degree 1. But remember, we have this virtual graph, right? With this extra bridge. And this is now the secret, right? Remember, now I can pick either one, C or A. That's right. So I'm back here. Pick something. Pick something of the green ones that is still in use. Well, I pick A. I'm going to be like really doing silly things, perhaps, from a perspective of what I really want, but I can do that. I pick A. Okay. Let me get myself a little bit extra space here. Okay. So here is A. And what is the path I'm going to take? From A to C, and then I return via the virtual bridge. So this is the one that I'm going to write like this. That's not really a path that I can use anymore. Okay? And then that's everything is gone, right? So now everything is gone, that and that. So, all right, okay. So now I put this everything together in the same way I always did. I go from A to B to D, and then in D I said, well, wait, I use D here, so I'm gonna make this little detour. Then I'm back in A, right? And then in A I have this path, and I go from A to C, but then I don't return, because this is the green bridge that I don't want to pick. So what is the path, the Euler path that I have? If I put it all together, from A I walk to B, that's the dark purple, and then I say, wait a sec, I have a detour, I have my pink detour, C, B, A, D. Okay, now I'm back. Let's do whatever you said, A, okay. And then the final one, I didn't really color this anymore, but okay, just for the fun of it. That was going from A to C, right? That was this one. So that is this bridge. And then go back over the green bridge, but I'm not supposed to do that, so I'm not gonna write it down anymore. So this is the last one, from A to C. So from A to C. And there is my Euler path. And this is from A to C, and if I want to go from C to A, just go backwards. Okay? So there is a solution, but it is not so obvious, right? I didn't draw it actually, right? So if we were to draw it, what does it mean? Let's do the detour part, right? So where did I take the detour? In D here. So when I was here in D with my, in this part here, I was in D, right? I should have taken my detour. Oh, so yeah, that's the problem, of course, with this. So let's... okay, let's do it this way. I'll draw the actual path now. Okay, so here we go. And I'll draw the actual path in red. Okay, so I was from A, went to B, then I in D, and in D said, okay, I'm going to take the detour. So instead of following this road, I'm now picking the pink road. You could think of this as walks in the city, right? In the guidebook, and say, okay, I'm going to go the pink one. Okay, now I'm back. So now I can oops. Yeah, it keeps doing this. Sorry. I have to stop once in a while, otherwise he thinks I'm trying to draw. Okay, so now I'm in D. Okay, D is, I can walk in D as much as I want, right? As long as I don't cross the bridge, I can walk as many times as I want. Okay, I go D. And what do I have to do then? Well, then you have to go to, continue on your first walk, the purple walk. Yeah, okay. And then what you have to do? Well, then you connect to the yellow walk. Okay, I do the yellow walk. And this is it. So, okay, yeah, there's a direction here that I should have drawn the direction, but okay, you saw me draw it, okay? Okay, so here's an application, and that's the last thing I will do, but it's gonna take me a little bit while too. This is a problem, a puzzle. So graph theory is nice for those that like puzzles and mathematical problems and so on, and they're not easy puzzles anymore. So this is called Mohammed's scimitar. Mohammed scimitar. Now, a scimitar is a sort of a type of sword that is curved. And Muhammad refers here to it's a Muslim name. It might even actually refer to the Prophet Muhammad, and so it is a sword that, or it's a picture that looks like one of these swords that you see in depictions of the Turks or the Islamic army or Islamic symbolism. It is just a picture. Here's the picture. I'm not very good at drawing, so I'm going to try to draw it. So it's basically two crescent moons drawn across each other. So this is the tip of the thing. Don't do this. Okay, so this is supposed to be only touching here. In this part, it's only touching, okay? So be a little bit. So this is the drawing, not a great drawing, but actually the problem is about drawing. And the question is this: can you draw this can you draw Mohammed Scimitar, this picture? Can you draw this without lifting your pen? I did that, right? As you saw me lift my pen, right? Because I'm very bad drawer, so I need like a lot of orientation. But the question is, can you do it without lifting your pen? And of course, without retracing, without going back on the same position. Okay, good question, right? So how are we going to solve this? Well, if we draw this thing, well, the way I drew it was I draw each of my big curves. But you see, that made me lift my pen 3 times or 4 times, depends on how you count it. But I could do also, for instance, this is an allowable draw. I could draw it this way and then draw this way and something. Oh, well, no, that I've done already, so I have to go back here. So you see that when I draw, at any time I have a crossing, this is now a no. I can change my direction. So I should think of all these crossings. This is a single crossing here. My drawing is a little bit off, but this is supposed to be single. And this is 2 crossing, and these are crossing. All of these I'm going to make into vertices. So we attach a graph to it. So any picture like this determines a graph where the nodes, let me do the nodes here, are all the possible intersections of this picture. So here, 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 here. I said this is one single intersection. Here, 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 and of course these 2 ends. Okay, so that's the graph. And the lines are now the edges. Okay, so let's calculate the degrees of this picture now. Okay, I'll do it always in red. So 2. Oh no, I want this kind of 2, 2, 1, 2, 3, 4, 1, 2, 3, 4, 4, 4, 4, 4, 4, 2, 2. I know not only can I draw this without lifting your pen, what this means in this case actually means, is there an Euler path? Because I start in one point, draw, and I might end in another point. So the question was weaker. Can I do this? Now, of course, I can do better. I can start and end in the same point because this has an Euler circuit. No alt degree, vertices. So there is an Euler circuit. In other words, I don't even have to worry about where I start. I can start wherever I want and I will get back to there. And now we do the same drawing part as before. Okay, now that takes a little bit of bookkeeping, and so we need to give some names. So I'm going to do A, B, C, D, E, F, G, H, I, J, and K. And so let's start at A, and I'm going to go in A, try to find a long. So you see, in the algorithm, you can pick any circuit. But let's think about it. The longer circuit I can find, perhaps if I'm really lucky, I find the actual Euler circuit, right? Don't forget, there is an Euler circuit. So if I pick a circuit, I could have picked the circuit that solves the whole problem, right? But most likely that's not going to happen if I just go randomly. But in any case, I'm going to try to pick a little bit long. So of course, what I'm saying, if I start at A, I could just return to A. But let's go all the way up and down. Okay, that's at least what you'd think one should do, right? So let's do that. It's a good source. Let's do it. So that means I go from A to C to E to H to I to J to G to F, and this is D here, right? D is a little bit out of place. And then F, and then D, and then I return to A. Okay? So what is effectively, therefore, I have erased everything. So let's mark all the ones that I visited. Again, I do it in blue. So from A to C to E to H to I to J to G to F to D. Okay, so I visit all these. So all the edges between them are now gone. I hope this is going to work, but probably not. No, it's not going to work, right? So I'm going to have to do it differently. I'm going to do red. I'm going to make them red, means I cannot use them anymore. Red means no passage, okay? So this, this, this are no longer available to me. So the only ones that left are the... And now, what is the next thing you need to do? Remember, you have now one circuit. It's not an Euler circuit, because there are still vertices left, right? There are still edges left, so still non-colored, non-red edges. These are... No, so what I'm colored, be careful. The red, true, it is my part of the circuit I had, but it means those I cannot not use anymore. Okay, those edges are no longer available to me. That's what it now means, because it's part already of that circuit that I made. Okay, so what I have to do is pick a new vertex, but with under condition. It has to come from one of the old circuit. So it must lie on that bottom like smiley face that I have now. Now that's almost everything except A and J. So I cannot take A and J anymore, but I can use, for instance, C. So let's start from C. So again from C. So this is, so here I picked A, and then I'm going to do step 2 and 3 at once. Okay, pick the starting point and then the circuit. So I pick A and AC. Now I pick C, and the path I'm going to talk to C is, well, let me walk again onto this upper crescent moon. Why not? So what I'm going to do, in other words, is I go from C down to B, then again, and then up the... So this is what I'm saying, right? This is what I want to do. And I will use edges that are all still uncolored. Okay, so here I go from C to B, then to E, from E to F. You say, oh, F, is that not a problem, Professor? You were there. Yes, vertices I can go through. I have to go to. I know to F I have to go to twice, because it's degrees 4. Remember, I will go there twice, half the degree. So I have to go to F, but I'm not using one of the red ones. I'm using two doors that are not closed yet. So from F, namely, I go to, I'm going, what I'm doing, the downwards, yeah, so to H, right? And then from H, I go to K, from K, I go to I, from I go to G, and from G, I go to H, and then from H, I'm back into C. Okay, and this is my path. Okay, so what have I used now? So make this also red. I used... This was the first one, this was the second one, this is the third one. Double check now. From H, K, I, J, F. Okay. Next, whatever vertex is still left, there's nothing left anymore. Everything is used. So here is my solution. Well, now I have to put... Right, so this the step 3 here, I didn't say this. So final step. In the final step, you put together. And the put together is the idea is you use your first walk, but when you get on a new path, on a possible new path, then you take that path first. Okay, so this would in our scenario, remember again, we went from A to C, but there we already have a new path, so we can use this new path already. So from A, I'm gonna, in other words, insert this whole thing in here. That's because I started at C, but I could have started anywhere on this thing. So suppose I did the same looping, but I remember here I picked C, right? But what if I had picked F? I still can have done the same thing. I would still have gone up and down like that and come back, but then it would have started with F. Okay, whatever you got here, this is the same thing, but then this is cyclical, right? So that would be this part. Well, replace this little f by this whole part, and that's it. You can do it at any stage. So this part would therefore be... I'm not going to write down the part, but I'll trace it out. So I should perhaps make 2 different colors, then I see it better. But okay, it's the upwards pointing moon and the downwards pointing moon. I started at A, went here, and then instead of continuing on my upwards pointing on my smiley face, I go to the grim, the sad face. I go this way. Now I'm back here, and I continue my walk on the smiley face. Where's my smiley face? This way. And if you notice, I did not lift my pen. Okay, so this is one cool application of Euler paths. Now, I also need to discuss Hamilton circuits and Hamilton paths, but I don't want to make this movie too long, so I'm going to put this in a separate movie, but also part of this lecture. But I want to keep things a little bit separate, so it's easier for you to go from one to the other.